OCE, Huntington Beach, a service of the Coast Community College District.
It's somewhat difficult for the human ego to admit that ours is an average planet, revolving around a nondescript star on the outskirts of a typical galaxy, just one of billions of galaxies in an unimaginably vast universe.
What is astronomy? That's easy. Astronomy is the whole universe. But it's a look at the universe from so far away that all the small details, like ourselves, disappear from sight. Astronomy is a study of the universe on its largest and grandest scales. And this is a source of both frustration and exhilaration for the astronomer. The astronomer tries to understand the universe scientifically. The idea is to put together a theory, that is an explanation, for whatever it is we see, like the craters on the moon, perhaps, or the motions of the planets, the light from the stars, or the shapes of the galaxies. And then astronomers try to test their theories against the evidence. Now, most scientists get to perform experiments. You nudge something a little bit, and you see what happens. But all an astronomer can do is look, and that's because practically everything an astronomer deals with is completely out of reach. But despite this limitation, astronomy gives us the opportunity to deal with very fundamental questions. We can ask, for instance, where did all of this universe come from in the first place? And where are all the stars and galaxies and ourselves going? Did it all have a beginning? And could it ever end? If so, what will that be like? Some things an astronomer looks at are simple and obvious: the rising and setting of the sun, the phases of the moon. And we've been recording our observations of these things for at least 4,000 years, since the time of the ancient Babylonians. And astronomical monuments were built at least 1,000 years before that. And we've probably been watching these things since the old Stone Age, 10,000, maybe 20,000 years ago. And whether it's the phase of the moon or the formation of a star, our preoccupation with the heavens has continued unabated. And that's nowhere as obvious as it is at a planetarium and museum like this, Griffith Observatory here in Los Angeles. Of course, our primary activity at Griffith Observatory is not research, but communication. Discoveries are made elsewhere. We report them here, but astronomical research is another matter. If we want to understand how we know what we know about the universe, and that is the itinerary of this series, then we're going to have to inventory what the astronomer sees and studies, from the smallest of interstellar dust to the largest of the galaxies.
The Earth is one planet in the solar system, one of a family of 9 planets, whose motions are dominated by the Sun, an average middle-aged star, which will generate heat and light for billions of years as it has for the past 5 billion years. The closest planet to the Sun, Mercury, is overwhelmed by its fiery parent. Mercury is a cratered, desolate planet, much like our moon. In the black, airless sky, 67 million miles from the Sun, is Venus. The surface of Venus is perpetually hidden beneath a deadly atmosphere of carbon dioxide and sulfuric acid clouds. Past Venus, 93 million miles from the Sun, is the planet Earth. Its great oceans form the cloud and irrigate the planet and nourish life. Its moon, about 1/4 the size of Earth, is almost as large as the planet Mercury. There is no air here and no sound. A footprint left here by our astronauts will remain undisturbed for millions of years. The next planet, 141 million miles from the Sun, is Mars. In years past, there had been imaginative speculation about the existence of Martians digging canals and managing vast farms. But no unquestionable evidence of life has ever been found here. Beyond Mars is the asteroid belt. Thousands of fragments of metallic rock. The largest is as large as the state of California, and the smallest no more than a grain of dust. Beyond the asteroid belt, more than 3 times the distance from the Sun than Mars, is Jupiter, the colossus of the solar system. More massive than all the other planets combined, Jupiter is, in a sense, a miniature solar system, orbited by over a dozen moons. At twice from the Sun lies the most elegant planet in the solar system, Saturn, with its remarkable rings encircled by dozens of moons. Far beyond Saturn, over 1.5 billion miles from the Sun, is the third of the giant planets, Uranus. Circled by a system of thin rings, Uranus rotates virtually on its side, a fallen giant. The last of the giant planets, Neptune, is more than 2.5 billion miles from the Sun. Neptune is accompanied by 2 moons, Triton and Nereid. The last known planet in the solar system, Pluto, averages almost 4 billion miles from the Sun. With its recently discovered moon, Charon, Pluto moves in a dim twilight of unimaginable cold. From here, the Sun is only a brilliant light in the night sky. This is the outer edge of the solar system. Traveling at 186,000 miles per second, it takes 5 hours for the light from the Sun to reach here. But consider this. It would take 4 years for the same light to reach the nearest star beyond the solar system. Traveling beyond the solar system to the nearest star would represent a voyage of more than 25 trillion miles, and our Sun is only one of several 100 billion stars, all bound by gravity and all revolving around the core of our galaxy, the Milky Way. Only half a century ago, our galaxy was still thought to be alone in the universe. Now we know it's just one of a local group of over 20 galaxies. And throughout the universe, there are more than 10 billion galaxies in clusters as far as the most sensitive instruments can reach. In a continuous cycle throughout the universe, new stars are born and others die. Some stars, after millions of years, deplete their reserves of nuclear fuel until only a white dwarf star remains, no larger than the Earth. When a star more massive than the Sun reaches what's called the red giant stage, its core collapses, raising its temperature by billions of degrees and triggering an unimaginably violent blast. A supernova exploding. What remains is an incredibly dense neutron core, so dense that a single tablespoon of its matter would weigh some 10 billion tons. The core begins to spin rapidly, emitting radio signals throughout its strong magnetic. Sweeps past the Earth, its pulse can be detected, and the star is. An even more bizarre death is predicted for the most massive stars. According to the laws of gravity, nothing can stop their collapse. The star virtually disappears from the universe, leaving a black hole in space. Its presence can be detected only by its influence on a companion star. Gases pooled from the visible star circulate around the black hole, and in a dizzying plunge, X-rays are emitted, which can be detected from the Earth. The gravitational pull is so intense that nothing, not even light itself, can ever escape this mind-boggling abyss. Although we know that this vast collection of galaxies we call the universe is expanding at a fantastic rate, the universe itself must come to an end. If there is to be no end to the expansion in time, the light of every star will be extinguished and the galaxies will disappear into infinite blackness. But if gravity halts the expansion, the universe will fall back on itself. Galaxies will lose their individual identities, stars will explode, and the endless sky will perhaps once again become a frightening blaze of light.
We're trying, of course, to do something very ambitious, comprehend the universe. We want to understand the things that are directly under our noses, as well as those things that are as far from us as our telescopes can possibly see. And we wouldn't have a prayer of doing this if we weren't confident that the laws of nature are universal. The helium atoms in this glass tube glow with light here on the Earth that's the same as the light they have when they glow in distant stars and galaxies. We can analyze that light in laboratories here on the Earth and compare it with what we find coming to us from those stars and galaxies. And it's the laws of nature and their universality that let us feel confident that we can know what those atoms far from Earth are doing. Now, it's not just the atoms in the stars and the galaxies that interest us. We care about the stars and the galaxies themselves, and for that matter, about the planets in our own solar system. Galaxies, stars, and planets all obey Newton's law of universal gravitation. Now, the way the old story goes, Newton was inspired by the sight of an apple falling from a tree in his garden in Woolsthorpe, in England. And the same law, the law of universal gravitation, that describes the way the apple falls from tree to earth, also describes the way the moon falls in orbit around the Earth, and the way the Earth and the other planets all fall in orbit. Because gravity follows the same rules throughout the Milky Way galaxy and beyond as it follows in our apple orchards, we can understand at least some of what we see going on in the universe far from Earth. If the laws of nature didn't work the same way everywhere and at all times, if they weren't universal, then we couldn't hope to comprehend the universe.
When most people think of an astronomer, they conjure up an image of a slightly eccentric stargazer who spends hour after hour throughout the night gazing up the narrow end of a giant tube of steel and glass. This is a very typical image, but it's just not true. Most astronomers are very normal, down-to-earth people who spend most of their time in the office or the classroom. And actually, astronomers spend fairly little time at a telescope. Well, a variety of different astronomical auxiliary instruments can be used to collect the light emitted by some distant celestial object. And so a few hours at the telescope can mean months, even years, of analysis of the data. For an astronomer today, a modern astronomer, back at the office means working with sophisticated electronic computers and other complex, intricate equipment. Even the telescopes a modern astronomer uses are unusual. For instance, an astronomer might use a radio telescope and walk into the control room of a radio telescope in the middle of the daytime and so never see the stars of the nighttime sky. And for that matter, the radio astronomer doesn't look through the eyepiece of a radio telescope, because a radio telescope doesn't have an eyepiece like an optical telescope does. Instead, the radio astronomer collects his data electronically. Some of the most interesting recent discoveries in astronomy have been made with radio telescopes. They collect invisible radio light from objects far beyond the range of even our largest optical telescopes.
The moon and the planets are our nearest neighbors in space. And yet until recently, it really wasn't possible to produce something like this globe of Mars in relief that's accurate right down to the intricate detail that we now know about the surface of that planet. We used to look at the planets remotely from Earth-based telescopes. Well, we still do, in fact, but now we send vehicles, spacecraft to other planets to even land upon their surfaces, and we ourselves have landed upon the moon, walked upon it, and brought back samples of it here to Earth. Our environment on the Earth depends a great deal on the sun, the nearest of the stars. And we've collected observations of the sun quite carefully for centuries with specially designed solar telescopes like this, Celestat. Well, it's important for us to study the sun, not just for itself, but also because it tells us a great deal about the other stars. And today, in modern astronomy, we look at the sun in colors that our eyes just can't even see. Ultraviolet and X-rays, and we're discovering that the sun is a much more mysterious and complicated object than we had first guessed. Of course, there are other stars besides our own sun, and in the planetarium theater we can duplicate the stars as we see them in the nighttime sky. And when we look with telescopes at the sky, we find, of course, that there are many more stars, billions of stars, in fact, within our own galaxy. Well, in modern astronomy, we're using new techniques at the telescope as well as high-speed electronic computers to reveal the details of the structure and the evolution of stars. Well, these new discoveries in astronomy are made possible because we've applied new techniques. And so modern astronomy is the era of radio astronomy and infrared astronomy and satellite astronomy, where we observe ultraviolet rays and X-rays and gamma rays. The really important change in astronomy in the 20th century is the discovery that galaxies like this in Andromeda are actually out beyond our own galaxy, millions of stars in themselves. We find that we're immersed in a universe of galaxies, and they appear to us in our telescopes in a spectacular variety of elegant forms. Well, the discovery of these tens of billions of galaxies around us transformed our viewpoint on the universe. We now know also that they're all traveling away from us, or at least that's how it looks, because the universe is expanding, and the farthest away of these galaxies seem to be traveling away from us at the very greatest speed. Well, we use the galaxies also to probe the universe. They allow us to reach out to the outer rim of visibility, and also, therefore, very far back in time. We're now using radio telescopes to look for something else in space, for signs of life among the stars, even signs of intelligent life. The idea that the universe contains other inhabited worlds is really not new. We've speculated about this at least since the time of the ancient Greeks. But what is new is that in this era, we do now know enough about the universe to know how to look for signs of life elsewhere. And with radio telescopes, we can begin the search.
Astronomy deals with things that are incredibly far away. So often all we can see, all we have to work with, is the faintest spot of light. Well, why should anyone concern themselves with such things? Can they really have an effect on us or the world in which we live? Why is it that astronomers study them?
I like to compare astronomy and other basic sciences with art. Both art and pure science are of no practical, enrich our lives and make life interesting and exciting. And that's the way I feel about astronomy. And I hope the public feels the same way.
I think that I sense that people feel it is one of the most important things that they can know and understand to understand this universe, and it's very complex, that they're just at the beginning of this understanding, and it's very fascinating, very exciting, and it has something vitally to do with themselves as human beings.
Astronomy is a so-called pure science in that it doesn't have direct benefits or particularly search for answers to applied questions which result directly in usable technology. On the other hand, if we ever succeed in making contact with intelligent life somewhere else in the universe, astronomy may suddenly become one of the most applied sciences around.
But I think thinking people have always been fascinated by the world in which they accidentally come to live, and I, for one, have always wanted to understand what it is. And this is a whole range of questions from the history of life on Earth, the history of our sun, and the remarkable thing that we on this planet, which we see about us as just land and buildings and streets and subdivisions, are in fact bathed in the outer atmosphere of that star up there, the sun.
To the professional astronomer, monetary awards usually aren't all that expensive jobs that I could be earning much more money at. But I can't think of a single job I could have where I could be paid for doing exactly what I want to do. It's a marvelous experience to work with students, to work at the telescope, to get brand new data that nobody's ever seen before, to study it and discover things about the universe. Those are the real rewards, I think. And I think to the layman who doesn't go into the profession himself, it's also a rewarding experience, just as an avocation, to learn something about the universe he's living in, the perspective he gains, the insight, not only to the universe itself, but perhaps to his own origins as well.
I have a very elaborate observatory up in the mountains, as you may know, but I'd like you to know that the amateur can work with the most fundamental equipment and do meaningful work with it. And that's how I started, with a 35mm camera, and that's where it's at. This is what astronomy is all about. And I cannot begin to tell you the even more profound feelings that come to you when you sit in a dark sky area up in the mountains and you look up at the sky. It is a mystery. It puts one in one's place on this planet. It makes one's worries seem rather insignificant.
The pleasure of being a scientist for me is the exhilaration that comes about from exploring the world of thought, from the recognition of a new idea, or at least an idea that's new to me, and methodology of discovering new ideas, and then testing those against physical reality by experiment. In that sense, it differs from religion or from mystical experiences, which also explore new dimensions of thought or feeling, but are not tested against physical reality. And so the pleasure of being a scientist is in participating in this mental exploration, but then being able to test it against physical reality and finding out whether nature really is the way I thought it was or not. That's the excitement.
On a personal level, there are as many individual motives for the study of astronomy as there are astronomers. And yet, ultimately, why should any inhabitant of the modest planet Earth bother with the study of a universe which is, for the most part, hopelessly beyond our reach? Perhaps the best answer exceeds the limitations of logic and reason. And the only justification needed is even a passing glance at the tantalizing visual treasury of the universe itself.